Hello everyone. So in the short video that you just watched, I showed how the my last project working, and in this video I just want to walk you through all the functionality of how it works. And if you later want to see like another video with a more detailed explanation on in any of the topics that I'm covering in this video, just let me know. So basically, this is the block diagram of what I have in this project. So I have a potentiometer connected to an ADC channel of the STM32 system on module. Um, and I'm reading that value and convert that to PWM signal to drive a motor. So according to the voltage read from the ADC, will control the speed of the motor, and we can monitor this using STM32 CubeMonitor. That's basically one of the main things that I want to show, because I really liked how or to use the STM32 the CubeMonitor to actually get quick visualizations of the data in the microcontroller without having to I don't know, create a complex application or without much struggle. So I'm gonna show you now basically how I configured the system on module to read the ADC values or the voltage values coming from the potentiometer and convert that to a PWM signal to control the motor. All right, so let's get started. All right, so here we are in I have the project already created on STM, the Cube IDE. I don't want to show everything from scratch because I don't want to bore you with the typing all the code, and I'm gonna post the code on my GitHub, so you can get download the code and use it as a template if you want to try it on your own microcontroller. So basically, the configuration for the microcontroller is so I have my ST-Link connected for debugging, and a crystal oscillator, external crystal oscillator, and the clock configuration. So the maximum frequency is 80 megahertz, and all the peripherals are working at 80 megahertz, including timers and all the other peripherals. Here you can see the ADC is also working at 80 megahertz with an external crystal of 24. So that's for my microcontroller. If you are using a Nucleo board or your own custom board, you might have something different here. You can use the internal high-speed oscillator if you want. And so basically the main the working principle is we are going to read ADC values or the voltage values coming from the potentiometer using the ADC. And in this case, I wanted to do the conversions of the voltage values using a timer event. So every certain time, the timer will emit an event, and that event is going to trigger the conversion of the ADC. And once we have the ADC reading, we'll get that reading and convert that value to a PWM signal, and from the PWM on to drive the motor, right, using the PWM signal. And we'll use a Cube IDE to read to monitor or read some internal variables on the microcontroller. So I have my prescaler set to 8, so that's bringing the 80 megahertz from the ADC clock down to 10 megahertz, and I have it set to 12-bit resolution. So here I have the scan conversion mode disabled because we have only one channel, so we don't need to scan for any other channels. And the continuous conversion is disabled because we don't want the ADC to continuously convert values, or we are gonna trigger the readings using the a timer. So, and end of conversion is end of single conversion. We have only one channel. So here's the important part for the timer. So the external trigger conversion source is going to be the timer 15 out event, and we are going to detect both rising and falling edges of the of this event, and we are sampling at 12.5 cycles and on channel 5, which is this one here, PA0. So I'm gonna later show you the how to calculate the conversion time of the ADC. And if we don't have also we have the interrupt enabled, so every time that we do a conversion, an interrupt will trigger, and that interrupt in that service routine will make some calculation to actually convert the PWM signal to I'm sorry, to convert the ADC value to the PWM signal. So on the timer 15, we check the configuration, timer 15. So with this configuration, we have set the internal clock to which is at 80 megahertz, and with these values, we are generating an event every 0.1 seconds. So if you see here, I have the trigger event selection, so to update event. So this value or this configuration is the one that is going to generate that event that is going to trigger the ADC and do the conversion. So, and once the conversion starts, the ADC is going to generate the interrupt, and in that interrupt service routine will do the conversion of the value. Also, to generate a PWM signal, I have timer 1. You can see here PWM generation on channel 1, which is PA8, and this is the signal that is going to drive the motor. So with this configuration, we are generating a signal at 1 kilohertz, and that's going to drive the motor. So basically, that's the configuration of the microcontroller. So if we see in the code here, on the while loop, we don't have any code. So because everything is managed by the hardware. So we only have a little bit of code on the interrupt service routine on both the timer. This is timer 16 just to drive the LED, so blinking LED that you saw when you watch on the at the beginning of the video. And here's the conversion. So let me just explain a little bit how we are doing this. So on the here I'm creating just two variables to hold the values read on the ADC and the duty cycle that we are going to write to the PWM signal. And also I'm defining here some constants, the minimum and maximum value of the PWM signal, which basically it's defined from 0 to 1000, but it's basically you can map or see these as the duty cycle from 0 to 100. So 1000 would be 100% of duty cycle, 500 will be 50%, and so on. And the ADC is the resolution of the ADC is 12 bits. So if we do the calculation, For 12 bits, we have a resolution of 4095. So that's a minimum of 0 or maximum of 4095. So we are going to convert this value to, or map this value to this range to this range here. And we'll do that with a function, or I define that function here, which is basically the same what Arduino map function does. And let me show you how this calculation is done. So that conversion is based on the straight line function. So here on the x-axis, we would have the inputs, which is basically the readings from the ADC, and the output on the y-axis is going to be the duty cycle. So according to this conversion of the equation of this line, we're going to map reading from here, and it will have an equivalency on the y-axis. And the way we do that is here. So this is the equation of the line. So this is how we calculate that equation. And if we solve these for y is going to be our mapped value, or the result of the conversion. And this is how we calculate the slope of the line. And if we substitute all the variables on this equation here, we'll get that the mapped value is going to be the PWM maximum, which is Y2, PWM minimum, which is Y1, ADC max, X2, ADC min, X1. And we're going to multiply that for the actual reading, the ADC reading, and subtract the ADC minimum, and at the end we just add the PWM min. So a lot of this conversion is a little bit simplified, because this PWM minimum is 0, as the same as the ADC minimum. So the equation at the end will be simplified to this, and the output will be from 0 to 1000. So if we checked the definition of that, or the implementation of that function, we have it here. And as you can see, it's just basically taking the value that we want to convert, the input minimum, input maximum, which is the ADC reading, and the output is going to be the PWM. So they convert the value using the formula that I showed on the slide, and then we'll return that value. So that's how the conversion is done. So if we go here to the initialization, here we just starting the timer for the ADC. So this timer is gonna trigger those events, and we call the calibration of the ADC. We give some delay here just to make sure that everything is correct, and we start the ADC with an interrupt. So now every time that this timer triggers the event, the ADC is gonna convert or take the reading from the potentiometer, and it will trigger an interrupt. And here we are initializing the PWM with the duty cycle of 0. And this is just for the LEDs, or the blinking of the LED. So we don't have here any code. If we go back again to the service routine of the ADC, so here we have the code that's gonna convert the value and actually write the PWM signal. So here we are reading the ADC, the ADC. So if, or when the ADC triggers this interrupt. It means that it finished the conversion. So here we read the value, get the value from the ADC, and map that value using this function to convert that reading to a PWM that we can write here on the fly to the timer 1, which controls the PWM signal outputted in the channel 1, and that's it basically. So now let me just show you how to work. We are going to compile. We don't have any error. We'll download the code to the board. All right, so now it is working. So now we can run. So every time that we compile our program, we have to update here the CubeMonitor so we can deploy, generate the dashboard, and now we can start acquiring data. So I'm gonna disable this. So here we are seeing the value read, or the raw value read from the ADC. You can see it's around 2600, around 50%, a little bit over 50%. And here we have the duty cycle, which is 65.5. So I'm gonna modify or turn the potentiometer so you can see how I'm decreasing now the signal, or we can increase the signal and we get a nice visualization of the data using CubeMonitor, which I think is really cool. And we are not like using the UART, loading the CPU, transmitting data, and this like a less intrusive method of visualizing the data. And we can basically get any data from the microcontroller, even the internal memory or any other variables that we have declared in the code. So here you can see you can decrease or go all the way to 100%, increasing the PWM signal on the output. And 99.9. That's the full scale of the output. So I hope that you liked the video, and let me know in the comments if you want to see more detailed explanation of what I just showed in the video, on or any other comments, suggestions, and well, thank you for watching, and until the next time.